Welcome. Before you start the video notes here, you need to have printed out your handouts from Canvas. Make sure that you've printed them out, cut them out, put them all in order. The directions are on Canvas if you haven't done that yet. So we're going to look at the layers of the planet starting from the crust. So we're going to not include the spheres that you've already looked at that were above the surface of the planet. We're going to start from our crust and we're going to move our way downward. So we do have multiple layers. We have a crust, a mantle, and a core. And as we move towards the center, the pressure is going to go up. The pressure goes up because of gravity. So as Earth is spinning, we exude a gravitational pull. And the things that are, as we spin like that, the heavier elements will sink towards the center of the planet. There's also the weight of the overlying layers that are pushing down and making it more dense as well. So we've got pressure as the layers are getting pulled towards the core, and that increases their density, which means that it removes the amount of space that's in between the molecules of an object. So if you think about a sponge isn't very dense. It has lots of air pockets and things like that, lots of holes. But if you think of a table is much more dense. You'll have those pieces are really close together. If it's a regular wood table, like a natural wood table, there's still going to be some spaces in it. If you end up with a laminate table and it has kind of that plasticky top, now you've gotten even more dense because you have less space between your particles. The temperature increases because of the function of pressure. So as you increase the pressure of on an object, you're going to increase the temperature of an object. That's based on the laws of physics. So when we look at how much of our planet is each one of these layers, the majority of our planet is in the mantle. It's in the middle part of our planet. The crust is very thin. If you think about an orange, and you think about, so there's the peel of the orange, and then there's that white layer that's part of the peel, and it kind of sticks to your orange, and you have to peel it off, that part. And then you've got the part that you eat, and then you've got the seeds. So imagine that an orange only had one seed in the middle, maybe two seeds stuck together. That would be like the core. Okay, the part that you eat would be like the mantle. And then that white stuff that we talked about that you have to peel off, that would be like the crust. The crust is not even nearly as thick as the peel of your orange. So you'd have to peel your orange in order to make this work. So it's not, the crust, while it supports the life for us, and supports all life on the planet, it's not the greatest part. We're basically on these big raft-like pieces that float around on our mantle. So we're going to start at the crust and we're going to work our way in. So as you're flipping through your little book, you should be on the page that's labeled crust up at the top. You should have gone through and labeled your different layers on there. So we're going to start with our crust. And once again, it's really not very thick. Now 70 kilometers may sound like it's a long ways, but that's underneath mountains is where we get that thickest part. It is rocky and brittle compared to the mantle and into the core. So our mantle we'll talk about as a plastic. It's very flowy. It's going to fill the shape of a container kind of thing. But the crust isn't going to do that. And as we move on in the semester and we start talking about earthquakes and volcanoes and how plates move around, this rocky, brittle component characteristic of the crust is going to become very important. We're going to talk about the different kinds of minerals that are in the different layers, but you'll see that there's a lot of similarities. Our lighter weight minerals are calcium, the sodium, aluminum. Silicate minerals are what make up things like quartz. A lot of our rocks are composed a lot of aluminum and silicate. These are lighter weight elements, and so they stayed up towards the surface, where the heavier ones that we'll talk about in a few minutes sank down towards the core. So we do have two kinds of crust. There's the oceanic crust, which is primarily under the oceans. Not all crust that's underwater is part of the oceanic crust, and we'll talk about the difference between those. But this is like if you're out in the middle of the ocean, most likely you're over the top of oceanic crust. It's a lot more dense than the continental crust because the weight of the water pushing down on the crust pushes the particles closer together, which eliminates the spaces, which makes it more dense. So it makes it heavier, And so when the continental crust and the oceanic crust meet, the oceanic crust is more dense, so it wants to slide underneath it. And we'll talk about later on in the semester about the landforms that happen and what do we see on the surface of the planet because the crust wanted to sink. You'll see that it's generally less than 180 MYO, means millions of years old. Um, so it tends to be the younger crust. And as we move further on and we start talking about plate tectonics and the age of our crust, you'll understand why it is that oceanic crust is a little bit younger. So that's something we'll come back to a little bit later in the semester. Our continental crust, you'll see it actually goes from that 30 to the 70 that you saw over here on this side. So I know it says 30 to 45, but it really goes to the 70. But once again, the 70 is underneath like the Himalayas. So we're talking about areas with really tall mountains to get to that 70 kilometers thick. So once again, it's less dense. This one has had air pushing down on it, but it hasn't had the ocean water pushing down on it. So it tends to be less dense. Now, there's varying densities of our continental crust based on what rocks they're made up of, and we'll talk about our different rock types this semester too, and we'll look at different densities of different kinds of rocks as well. And our continental crust tends to be our older crust. So Earth is about 4.5 billion years old. It took a little while for Earth to cool off enough to actually make rock, and that's why you'll see some of the oldest rocks that we have are around 3.8 billion years old. So the BYO is billions of years old. After we pass through the crust, if we were to do that, now when we go back, hang on one second, we're going to go back. This is the furthest we've gone down, is into the crust. We've got some diamond mines that go about a mile or so deep, a little bit more than a mile deep, mostly in South Africa is where some of the deepest mines are at. And we can't really get down much further. Because remember, as we said, the heat increases as we move towards the center of the planet, and that doesn't mean that just as you pass through the crust, then all of a sudden you're in the mantle and it gets hotter. It gets hotter as you go down in the crust. And so when you have these really deep mines like that, the temperature increases dramatically. And so in the bottom of some of these mines, it can be in excess of 120 degrees Fahrenheit, which makes it really difficult to do anything, and it makes it difficult for machinery to work. And so we haven't gone much further down in the crust than some of those diamond mines. So we have never actually been inside the mantle, which is our next step. So our mantle, once again, there's different parts to the mantle that we'll talk about here in just a minute. It is pretty thick, but I want you to look at, so our crust was from 3 to 70 kilometers thick. And when you look at our mantle now you're talking about almost 2,900 kilometers thick. So we're talking about significantly bigger area. It takes up a significantly bigger volume as well because it's going all the way around the planet plus that deep. So you're talking about a lot of volume. The consistency is called a plastic. So a plastic is something that acts both like a solid and like a liquid. And the example of silly putty is on here. So if you've ever played with silly putty, you know how when you first get it and it comes in that egg, and you have to like scoop it out of the egg because it's actually formed an egg shape inside. So it flowed to match the shape of the container, and that's a property of a liquid. If you think about that, you put water in a cup, it's going to fill the cup up till the level of the water. So it has some properties of liquids. It also has some properties of solids. So if you strike silly putty sharply and hardly, so if you put the silly putty like on the concrete floor or something like that, and you make it into a ball, and you were to take a hammer and you were to hit it hard enough and fast enough, it has to be very hard and sharp, you could actually cause it to break. Okay, and not just like squish out from underneath your hammer, but you could actually cause it to crack, and that's a property of a solid. So it has properties of both liquids and solids. It's a really, really thick liquid. You'll see that it shares some commonalities with the crust as far as our composition. You're going to see less aluminum in here. Aluminum's really lightweight, and so it mostly floated up, but you'll see some. You'll see over here, you see a little bit of aluminum in there, but you're going to see a lot of the same elements that you see in the crust. It's just here it's too hot for them to stay solid. So we do have our different zones of our mantle. The lithosphere is the top part, so we come down from the crust, and then we come to the lithosphere, which is the top of the mantle. And so it is solid in this part, and you can see that it's about 100 kilometers thick. So we have, but it's really hot in there. Once again, we have not been into the lithosphere. The asthenosphere gets below that, and now we have our plastic properties. And it's going to stretch from that 600 kilometers down to where our 2,800 kilometers, because everything past the asthenosphere is part of it, is part of that larger part of the mantle, all the way down until you get to the core. So we're going to look at our core. We do have an inner core and an outer core on our planet. And we're going to start with the outer core, so I apologize in your notes. I know they might be backwards, but make sure you're looking at your labels. So our outer core is a liquid. It's too hot to be solid. It's too hot to be plastic at this point because it's getting down towards our core, which is having radioactive decay is occurring in our core, which is it's what's generating all that heat. And so you'll see that the composition changes though. So we had in our mantle, we had our sulfur and our oxygen, right? So we still have that. But you'll also see we're adding in metals. So Fe is iron, Ni is nickel, and we have an iron-nickel core. And so you start to see a lot more of these denser elements in the outer core. And you'll see that the temperature is pretty hot in there. So you've got it both in Celsius and in Fahrenheit. Think about a really hot day here in Arizona where, you know, it's like 115, 116 degrees and it's really, really hot. Now think about 7,200 degrees Fahrenheit. Okay, that's hotter than anything that we can make here on the planet. As we step down from our outer core into our inner core, now it's solid, but it's still hot, like, right? It's hotter than it is in the outer core. But the gravitational pull is so strong at the center of the planet. That's where the gravity is the strongest. And because of that, it makes it into a solid. So it's not the hot part gets outweighed by the gravitational pull. And once again, you're going to see that now our sulfur and oxygen has left. And now the majority of our core is iron and nickel. And the temperature has gone up dramatically. So the outer core, so Earth spins like it is on the guy's finger here, or was a second ago. So Earth is spinning around, and anything that is not firmly attached to the planet doesn't spin at the same rate as everything else on that planet. So anything that's a liquid tends to move at a different rate. Okay, so our oceans, the air above the planet that's held in place by gravity but isn't actually firmly attached, those spin at a different rate than the planet does. And the outer core and the inner core, for the same reason, don't spin at the same rate. And because of that, there's friction between the outer core and the inner core. And there's iron particles in both the outer core and the inner core. And when we rub iron particles together, we get a magnet. And so magnetism on our planet is really important because that's what holds we exude a magnetic field around us, and that helps to protect us from the sun. So the fact that we spin, okay, gives us gravity for one thing, okay, and it also creates this magnetic field. If you want to think like sci-fi land, think of like a shield around our planet, because that's basically what it is, that reflects away some of some of that radiation from the sun and helps to protect us. So magnetism is super important to us. If our planet were to stop spinning, we would have all sorts of issues, but one of them is that we would lose that magnetic field. Just one more look at the inside of our planet. So on that top sheet, if you want to, it might be a good idea just to sketch. You don't have to, doesn't have to be beautiful. It doesn't have to be perfect. It doesn't even have to be in color. But you might want to do just a cross section of the planet where you show your core, your mantle, your crust, show approximate thicknesses. Once again, it doesn't have to be beautiful or perfect, but you shouldn't show your crust taking up half the planet. Okay, so you want to show your crust being very thin, mantle taking up most of it, inner core, outer core.